free.
Yeah, PGP was pretty good privacy.
Which is a misnomer because it's actually really good privacy if you do it right.
Yeah.
So,
But there was a time when you didn't want to tell people that you had really good encryption because encryptions were considered munitions. And if you exported a program that did encryption to another country, you could be charged with exporting munitions, guns, and weapons to a foreign government. And bad things could happen.
what's the status on that nowadays? Do they still? Because I keep seeing those. Yeah.
I think everything's there, so.
I mean, I went to Germany and they asked me if I had any, and they gave me a little shoot gas if I had any of these things on my phone.
Oh, really?
Yeah.
Interesting.
So I checked the box and said no and laughed a little bit.
Yeah. Oh, I don't know what this means.
I'm taking a check.
What are they for this?
They asked if I had certain kinds of encryption or it was also like state secrets and things like that.
Yeah.
Yes, I'm bringing state secrets into Germany.
Anybody here remember using Netscape?
Vaguely.
Vaguely. Netscape came in two versions. There was like a 56-bit encryption and I think 128-bit encryption. And the smaller encryption key you could export. But if you wanted the stronger encryption, you had to like agree to all these things. That you were a U.S. citizen, you wouldn't export it, and you wouldn't use it for things outside the country and all this stuff. Public key encryption was an interesting history. I talk about it a little in 120 sometimes, when the mathematicians and graduate students who discovered this decided to publish their results, and the government threatened them with imprisonment. Yay. 3 hots and a cut. All right, any questions from up to here? So, Hilbert's Grand Hotel.
I was hoping you'd start with that.
Yes.
It's just infinite. You just put more people in there. You can't fill up infinite.
Well, which key do you hand to the new guest?
What?
I don't know.
You just move people.
You can hand them key 1, and the person who's in room 1
Goes to 2.
goes to 2, person in 2.
Or you could do the easier solution, which housekeeping can handle, and you just move the door numbers. Numbers on the door, and you don't have to
That's
have
true.
your guests move them.
That's true. Same way though. So we can put the new guest in room 1, move 1 to 2, 2 to 3, 3 to 4, and because there's an infinite number of rooms, we can do this, and nobody's going to be displaced. So what does this mean? We have this set G of guests, and there's an infinite number of guests. So G is an infinite set. So G equals set of all guests, which is infinite. And then after your new guest comes, we have G prime, which is like G union with, I don't know, Tom, whoever the new guest is. And that's also an infinite set. But since both of these sets perfectly fill up every room in the hotel, in some sense they're the same size. They have the same number of guests. And that's a notion we want to make precise today. The notion in which this infinite and this infinite are somehow the same size. And this is this thing we're going to call cardinality. So if G is an infinite set, cardinality is some sort of measure of G's size. And in the case of Hilbert's Grand Hotel, it's going to turn out that the cardinality of G is this thing that we call aleph naught. It's a symbol we use to represent the cardinality or the size of the number of guests staying at this hotel. And incidentally, if a guest checks out from room 17, can we do something so that all the rooms are occupied?
Move everything from 18.
Move everything from 18 forward, down one room, put person from 18 into 17, 19 into 18, and again, every room will be occupied. So you can keep your no vacancy sign on. So adding or taking away a single element from this infinite set doesn't change its cardinality. Suppose Hilbert has a second hotel across town, and the water pipe breaks, and then those guests have water, and they all decide they want to come and stay at your hotel that's already filled. Can you fit an infinite number of new guests from this other hotel?
Sure you can.
You could do something like have each person move into every other room, so your guests only take the odd numbered rooms, and then you take all these guests and you put them in the even numbered rooms. And that would work. So even the union of two sets of this size is still the same size, the same cardinality in some sense. And again, this is not the number of elements, because that's infinity and that's not a number. But it's some notion of the size of these things. And the definition of aleph naught is actually the cardinality of the integers. But if we have an infinite number of rooms starting from 1 and going up, that's half the integers. And we just argued that if we had two sets of those, say the integers from -1 going down, and then we added one more element, say 0, that gives us the set of all integers that's going to have the same cardinality. So the cardinality of the integers is aleph naught. And it turns out the cardinality of the odd numbers is aleph naught. The cardinality of the set of primes is aleph naught. What about rational numbers? And I spoiled this already a few days ago. Cardinality of rationals. Rationals are fractions. Some integer divided by some other integer. So let me give you a definition of what it means to say that two sets have the same cardinality. So cardinality of A equals cardinality of B if and only if there exists a one-to-one correspondence between the elements of A and B. And this is for A and B infinite. I think it technically works for finite, but we're just going to talk about infinite sets today. So if there's a one-to-one correspondence between the elements, then we say that they have the same cardinality. So for example, all positive integers, even positive integers. Is there a way to find a correspondence between each element here with each element here? A function or a mapping that uniquely identifies each element here with one element here, and each element in the second set with an element in the first set. Yeah, we could just say multiply by 2. And 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8, and so on. And if we think about it, any two elements here that are different will map to different elements here. And any element in here is even, so it must be 2 times something. So it corresponds to the number that's half its value. It's a perfect one-to-one mapping. And because of that, we can say the cardinality of this set is the same as the cardinality of this set. And if we believe this, the cardinality is transitive, and we can convince ourselves if we think about this definition, because if there's a one-to-one correspondence from elements here to here, and from here to here, we can put those mappings together and find a one-to-one correspondence between A's elements and C's elements. So since we know that this has the same cardinality as the integers, if we pick any other set and it has the same cardinality as the integers, it's going to have the same cardinality as this set. And in fact, any two sets that have the same cardinality as the integers have the same cardinality as each other. And we're actually going to pick the positive integers as a convenient set to compare an unknown set to. So if we have some arbitrary set S and we want to know if it has the same cardinality as the integers, we can ask, is there a one-to-one correspondence between the elements of S and this set? And if we have some set S, with some weird set of elements in it, and we want to know if it has the same cardinality as the integers, in other words, cardinality L of naught, it would suffice to find a one-to-one correspondence between here and here. And we can do that if we have a way to order these and count them. Whatever 1 maps to, we call that the first element. Whatever 2 maps to, we call that the second element, and so on. So anytime we have a set that we can count, 1, 2, 3, 4, 5, 6, and so on, and know that we're going to cover all the elements, that set must have the same cardinality as this.
Okay, so 2 things. First off, cardinality, could that be represented with an integer? Because it's the size of the set, so...
For a finite set, it is an integer. It's the number of elements.
Okay. And secondly, could we use like a piecewise function? Where if it's x is 1, then it's a, if it's 2, it's dog, and
absolutely. Yep. Any way that you have to define a correspondence will work. Did you have a different question? Okay. So, in this sense, if we can count the elements of a set, it has the same cardinality as the integers. And so we get a definition or a terminology. The set S is countable if its cardinality is L of naught. And to know if we can count the things in a set, all we have to do is be able to order them in some kind of sequence. Sequence implies there's a first thing, a second thing, a third thing. There's your correspondence. Yeah?
So you say the set is countable if the cardinality is L of naught. I thought the set was infinite.
It is infinite. Let's continue an infinite set. Let's just keep talking about infinite sets. So an infinite set S, we can call it countable if its cardinality is L of naught.
But you just said you couldn't count an infinite set.
Countable is a definition, it's a term.
Oh.
It doesn't mean that it's got a number.
I see.
Okay, so this is a definition.
You could give it a number and you'd be able to find something in it.
Right. So we call a set countable if. Yeah?
Could you explain how that how S has the same cardinality as, what is it?
Well, I don't know if it does.
Oh,
But
okay.
if I continue this and I could say, okay, this is element 1, 2, 3, 4, 5, 6, and I could, for any element in here, I could say this is element 5416, right? If I can find this mapping from these integers to these elements, and it covers exactly this set of elements, then I know it's countable.
Okay.
Okay, and it may not be something like just multiplying 1, 2, 3, 4, 5. It might be something different, like prime numbers. Right, here's a set prime. But I know that for any number in here, I can say that's the 2 millionth prime. That corresponds to 2 million. And for any number in here, like 80, I can say I know there's an 80th prime. There's a one-to-one mapping from that set to this set. So the cardinality of this is aleph naught. So now we can look at the question of rational numbers and ask, is there a way to count the rational numbers or to order them so that we can have a notion of the first, the second, the third, the fourth, and so on? There actually is. It's a cool little trick. So a rational number is a fraction. It's one number, one integer divided by another. So let's do the following. Let's write down integers. And let's fill in these boxes with the number on the left divided by the number on the top. So this is 1 over 1, 1/2, 1/3, 1/4, 1/5. This is 2 over 1, 2 over 2, 2 over 3. What? And we fill in all these boxes. If you think of any rational number, and we're just worried about positives for now, let's not worry about negatives. Any positive rational number, will there be a box somewhere corresponding to that rational number? There's gotta be. If your number is p over q, go down to row p, column q, that will be p divided by q. And there are numbers that will appear more than once in here. For example, 1 over 1, 2 over 2, 3 over 3, those are all the same number. That's not going to worry us, though.
Doesn't that happen in every diagonal?
Yes, it does, because the whole diagonal is always 1. But if this collection of things is countable, then certainly a subset of it is also going to be countable, because it's got fewer things. So the question is, can we make this collection of things in this 2D matrix somehow correspond to the numbers 1, 2, 3, 4, 5, 6, 7, and so on? Can we order them? And we can. And one way to do that is start here, move over, come down, go up this diagonal, go across, come down this diagonal, come down, go up this diagonal, go across, and so on. And I'm going to number these elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on.
That's the way that certain image files are encoded, right?
Yeah.
Yeah. Alright.
It's a convenient way to hit every pixel in the case of an image, and to just think of it as a big, long, linear ordering of information. With an image, we could do a raster scan, but that wouldn't work in this case because our first line goes over forever.
But isn't it 1-to-1? So if we encounter the same thing again, that wouldn't necessarily be 1-to-1.
We could just skip those. We could say this is 1, 2, 3, recognize this as a duplicate and skip it, make this 4, 5, 6, 7, I don't know where the duplicates are. We could just skip over those. But we could also just say, let's try to make this whole thing countable. And if it is, then something smaller than that, which we get by removing the duplicates, is also going to be countable. So this gives us an ordering on the rational numbers, which means we can find a one-to-one correspondence between the positive integers in every block, which means the cardinality of this is Aleph naught. So the cardinality of the rationals is again Aleph naught. So lots of things are countable.
Like, in this case, what would 2 over 2, what, like, number would that, what?
If I didn't worry about duplicates, 1, 2, 3, 4, that would correspond to 5.
Oh, okay.
So just start here and follow the path and count how many blocks you go through. And any block on here, eventually I'll visit it. So it corresponds to a number, and for any positive integer, I just go out that number of steps, and I'll get to one of these boxes.
So what would a situation be where it's not countable?
Good question, because everything we keep coming up with is countable.
Rationals?
No, irrationals.
Irrational.
Irrationals will turn out to be uncountable. And a slightly nicer case to work with than irrationals is just a set of real numbers. And the set of real numbers has cardinality bigger than Aleph naught. We haven't defined what we mean by bigger, so I'm just going to say it's not the same as Aleph naught. There's no one-to-one correspondence between integers and rationals.
Because there's infinity real numbers in between two given integers.
There's infinity rational numbers in between two given integers also,
Yeah.
but the rationals are countable.
Well, but by definition, if we do all real numbers, which includes irrationals, they can't be expressed as a ratio. So
Right.
you can't do that same trick.
So we can't use this trick, but how do we know there's not another trick we could use?
I'm gonna go with, because you just told us. I have no idea, honestly.
And it's a fun exercise to try, right? And you can think of taking the decimal representation and first taking all the one-digit numbers and then all the two-digit numbers and all the three-digit numbers and just ordering those as if they were integers and hope that eventually you get to every number. But it turns out you can't do it. And I think we have time for a proof of that. Let me show you the proof for this, because it's a really powerful style of proof. And if it doesn't ring 100% clear, that's okay. But let me show it to you, and you can think about it, and we can talk about it more another time. Let's prove this by counterexample. Suppose, so here's our proof. Suppose the contrary, i.e., suppose the real numbers are countable. That means there's a mapping from positive integers to every real number, and it's a perfect one-to-one correspondence. So let F be our mapping. From positive integers to R. So I can make a table as follows. The number 1 corresponds to our first real number. I don't know what it is. And let's just do real numbers between 0 and 1. Let's make it even easier on ourselves. Let's suppose that the set of real numbers between 0 and 1 are countable. And we're going to show that even that is not true. So suppose cardinality of the set of real numbers between 0 and 1. So let's just suppose that the number 1 corresponds to 0.51436178, blah, blah, blah. And the number 2 corresponds to pi minus 3. because that's a real number between 0 and 1. And the number 3 corresponds to, I don't know, 0.5. And the number 4 corresponds to 1/3. And so on. And you claim that you have a table like this. And for any integer, positive integer, there's a real number corresponding to it. And any real number between 0 and 1 is somewhere in this table and corresponds to an integer. Okay, that's our claim. We're going to show that cannot be the case. And it's a really clever argument. So here's what we do. We take the number that corresponds to 1, we look at the first digit and we increment it. And we write that down here. And we look at the number that corresponds to 2.1415, we take the second digit and we increment that. And we write that down here. And we take the integer that corresponds to 3.500 and we take its third digit and we increment that and we write that down here. And we take the element that corresponds to 4.3333 and we take the fourth digit and we increment that and we put it down here. And we keep doing this. And we come up with a new real number between 0 and 1. And so this number must be somewhere in this table.
As for number 2, did you circle a 1 or a 4?
A 4.
It didn't go quick.
That's a 4. So we have a new real number. It must be somewhere in this table, but it can't be in this table. Because if somewhere in this table, say number 5,432 was this number, in position 5,432, whatever digit I find here, I'll find a different digit here. Because I incremented digit 5,432 of this number to get digit 5,432 of this number. So no matter what number I pick, it's going to differ from this number somewhere. In particular, if this claims to correspond to the integer n, this and this will differ in the nth digit. Conclusion, this number cannot be found anywhere in this table. So there's no integer that corresponds to this. So we can't find a one-to-one mapping from integers to reals, and so the cardinality is not equal to Aleph naught. And then if I add in all the other real numbers, I'm just going to get a bigger set, and that's certainly not going to have cardinality Aleph naught either. It's going to be bigger in some way.
I think I got this part, but I didn't get how this proves that one.
Because if I suppose the contrary of this, which is that this is equal to Aleph naught, then there's a mapping from positive integers to this set, which means I can make a table like this. But if I'm given a table like this that you claim is complete and contains every real number, I can show that it's not true because I can find a real number that should be in this table but isn't.
Sounds really similar to the infinite primes proof.
In some way, yes. And this is a general mechanism that is powerful. So infinite primes is a proof by contradiction. This is a particular thing called diagonalization.
I mean, you're generating a number from the thing that you're given, and then you see that it doesn't exist in the set
Right.
that you're saying. So, I mean, what would that be called? Because that's the same sort of a concept.
That's a proof by contradiction.
Just a proof by contradiction?
Yeah.
That's all they
Because
call
you
it?
assume you've got the complete set and then you generate something that's outside the set. It may have some other name, but I'm not familiar with it. But this particular proof by contradiction uses this idea of diagonalization, of somehow moving along a diagonal somewhere. It's actually called Cantor's diagonalization argument. And he gets credit for proving that reals are uncountable. So we have at least two cardinalities. Aleph naught, cardinality of the integers, and cardinality of the reals. And we can define operations and facts we can do with cardinalities. For example, the union of two countable sets is countable. The intersection of two countable sets is countable, and so on. I don't want to go there right now. But the important part, or the significant part, is this. We can prove, but we won't, that there exists, in some sense, a smallest set. I don't know, let's call it T, with cardinality bigger than Aleph naught. We still have to say what we mean by bigger or less than. But we know that there exist sets with cardinality different from Aleph naught, bigger than Aleph naught. We can prove that there's actually a smallest such set. The question is R this smallest such set? Or is it possible that there's some set with cardinality bigger than Aleph naught, but smaller than R? And so far we only know two cardinalities. Cardinality of the integers, cardinality of the reals. Is there a set somewhere in between those? That question is called the continuum hypothesis. And the continuum hypothesis claims that there is no set in between those. If you keep adding more things, it's still countable, it's still countable, it's still countable. As soon as it's not countable anymore, it's got the cardinality of the reals. And we can find things with bigger cardinality than the reals, things larger than this that we can't map one-to-one with the reals. But can we sandwich something in between Aleph naught and the cardinality of the reals? Continuum hypothesis says yes. Famous question. Prove the continuum hypothesis. There is no proof. It's an undecidable proposition. You can't prove it, you can't disprove it. That's been proven. So it's undecidable. So the continuum hypothesis is undecidable. Well, what does it mean to say we can't prove it? You and I can't prove it. A computer can't prove it. Somebody who studies math for 5 centuries can't prove it. Nobody can prove it. Right? It's been proven that you cannot find a proof for this, but you also cannot find a counterexample. And that's weird. But we should be precise, is undecidable under what's called ZFC, Zermelo-Fraenkel choice, the set of axioms under which we normally do set theory. There are other axioms under which you can do set theory, but the one we do is something called ZFC. And this C, this means choice. We assume an axiom of choice. What's an axiom of choice? If you have a set of elements, there's a way to pick an element from that set. That's the axiom of choice. Can't be proven, can't be disproven. That's weird. If you give me a set of things, I can pick one. You give me a box with 5 things, I can pick one. You give me a set with an infinite number of real numbers, I can pick one of those numbers. But can you prove that it's always possible to pick one of those things? No. And you can develop set theory assuming that you can't always pick an element, and you can develop set theory assuming that you can always pick an element. And you get to different places. But you can't prove it or disprove it. You have to assume it or not assume it. So ZFC assumes we have this magical choice function that can pick an element out of a set. If your set's countable, we can always pick one. We can say, take the number that maps to 1, that's the element I'll choose. If it's uncountable, how do we do that? if we have a set like this, all the reals between 0 and 1, not including in 0 and 1, we can't say pick the smallest element, we can't say pick the biggest element, so we can't really say pick the middle element. And you and I could do it, I could just pick 0.5, 0.2, whatever. But to prove that you can always find a function that picks some element from this set, can't be done. It's an axiom, it's something you assume and then you build from there. Kind of like parallel lines never intersect. That's an axiom. Yeah?
Is there an axiom where the continuum hypothesis is decidable?
I was wondering that as I said that. I don't know. I don't think there's a proper form of set theory where it's decidable. You could find some degenerate form where you have some weird set of axioms, and it might be possible, but I don't know. Look that up. I'm curious. So cardinalities don't act the way other things act. It's tempting to think of them as numbers, or we let infinity be a number and this is infinity plus something, but that can betray us. We can't think of them as just the number of elements in an infinite set. It's just an abstract notion of size. But we have to let go of our insistence that we can count the number of things in a set, because it doesn't work for countable sets. So there's a theorem called the Schroder-Bernstein theorem, which talks about inequalities. So let me give you a definition. We'll say that the cardinality of A is less than the cardinality of B if we can find a mapping from elements of A to elements of B, and it's got to be a particular mapping. It's got to be a one-to-one mapping. And when we talked about equality of cardinality, we were talking about both directions, a one-to-one correspondence. Every element here corresponds to one element here and vice versa. But we can talk about just a one-to-one mapping, which says each element here maps to one element here. But there may be elements over here that aren't mapped to. So for example, we can show the cardinality of Z is less than or equal to the cardinality of R. It should be less than or equal to. By saying we can take the numbers 1, 2, 3, 4, 5, and we can just map those to the real numbers 1, 2, 3, 4, 5. Right, there's a one-to-one mapping. We know that there's numbers here that we have not mapped to. That's okay. We're only showing that this is less than or equal to this. So we can find a mapping from each element here to a unique element here, but we may not map to every element. So this shows that this is less than or equal to this. But it could be equal also. So here's a theorem. If cardinality of A is less than or equal to B, and cardinality of B is less than or equal to A, then the cardinality of A equals the cardinality of B. That probably seems reasonable because we're using less than equal and we're using equal signs, but these aren't numbers. This is this abstract thing we call cardinality. And it's saying if we can find a mapping from set A into set B, and we can find some possibly different mapping from B into A, then we can find a one-to-one correspondence, and they have the same cardinality. That is difficult to prove. It can be proven. It's called the Schroder-Bernstein theorem, but it's not obvious. And let me give you an example of this. Here's one set containing all the real numbers between 0 and 1 inclusive. Here's another set containing the real numbers between 0 and 1, but not including 1. Do you think they have the same cardinality? Probably, because we're just adding or taking away one element. But can we find a one-to-one correspondence between these numbers and these numbers? That's tricky. And it's a fun thing to try. But if we start with this set and we want to add one more element, where can we put that in our correspondence of these elements? And this is Hilbert's Grand Hotel with a real number of rooms. And one more guest arrives. You can put them in the hotel. But coming up with a formula for which room to give them, that's tricky. I don't have an answer for that. You can't put them in room 0 because then the guest who's in room 0 needs to go somewhere. And there's no next room. If there was, this would be a countable set. We have the first room, the second room, the third room. So where do we put this new guest 1 in this collection of guests? I don't know. Nonetheless, we can prove that these have the same cardinality by using the Schroder-Bernstein theorem. All we have to do is find a mapping from here into here. And that's easy. We can take each number divided by 2. 0 maps to 0, 0.1 maps to 0.05, and this number 1 maps to 0.5. So the cardinality of this is less than or equal to this. And we find a mapping from here to here. Well, we can just map each number to itself.
That's if we start from 0 and go to 1. What if we start from 1 and go back to 0?
I think you still get stuck at the end.
But I mean, we're gonna start at the first. Like, we don't have room for the first one. Or do we?
I think if you think of them in a different order, you still have this problem. You end up with one guest you got to put somewhere. But Schroder-Bernstein will let us show that these are equal, because we can find a map from here to here, we can find a different map from here to here, and then we can say Schroder-Bernstein and conclude they have the same cardinality. Even though we can't construct a one-to-one correspondence. I don't know if it's impossible to construct it, but I haven't been able to. I haven't tried much. So there are things that are true that may not be obvious how we can show them. I read this the other day. It was a theorem. Every number you've never thought of, every positive integer you've never thought of is bigger than 100. Is that theorem true? Any positive integer that you have not yet thought of is bigger than 100.
Oh.
Assuming you've already thought of the numbers from 1 to 100 sometime. Any number you haven't thought of, it's got to be bigger than 100. You cannot find a single instance that demonstrates that, though. Because if you try to say, sure, here's a number I've never thought of. Oh, I just thought of it. Never mind. So you can't demonstrate that by example, but nonetheless, you can prove that it's true. That's unrelated. But maybe not. All right, one more oddity, and we'll call it a week. How many C programs are there?
Infinite.
What kind of infinite?
An infinite.
An infinite. Let's allow C programs to be infinitely long. We have no memory limitations. Are there a countable number of C programs or an uncountable?
Right now, I would say you could count the number of C programs that exist. The amount of possible C programs.
Countable or uncountable?
Hey,
Whoa, do we have pizza or something?
yeah, it says room 10, 210. Have I got the wrong room?
APH?
Yeah.
I missed the ECS
I
club.
think you're an hour early.
Oh, it might be for the ECS club.
Nice time.
I'll try where I usually go.
Okay,
All right, thanks.
come
Sorry
back
to bother
if
you.
not.
Sorry to bother you.
I'll have pizza.
Talk about
I think it's
that.
next
Guys,
class.
an hour, 20 minutes.
Well, the next
I'm gonna go.
Next class is mine.
You could make for memory, but since we have.
So if memory is not an issue, if you're allowed to write a program that's an infinite number of characters long, is the total set of all C programs finite or it's infinite? Is it countable or uncountable?
Possible C programs?
Yeah.
Or existing?
Possible.
Oh, that sounds pretty infinite.
Definitely infinite. Can you order them? Can you count them somehow?
All you have to do is the same concept you use for brute forcing a password. You just
Yeah.
go start with one character and
Yep.
then
Here's my first C program, here's my second program, here's my third, and so on. Here's my 27th program, here's my 28th program. I need more than just letters, but you get the idea. I can just order my characters. Hey, they're already ordered. It's called the ASCII code. I can write 8 bits for each character. And if I have 1,000,000 characters in my program, that's 8,000,000 bits. That's an integer. And it's a unique integer. Each integer corresponds to some set of characters, a C program, probably with syntax errors. And each C program corresponds to an integer. It's a countable set. So there's an infinite number of C programs that we can write, but it's still a countable infinite. All right, I'll give you an example Monday of a function that we cannot write in C. A fundamental limitation of what we can do, even with an infinite length C program. Because we're going to show that the possible number of functions we could write is uncountable. And so there's more, in some sense, than there are C programs. And somewhere there's a function that no C program maps to. We'll play with that on Monday. Your homework is posted on Canvas.
Now that you've blown our brains.
Now that I've blown your brains, you can recover over the weekend and work on your homework. I don't remember when I made the due date. Check Canvas. I put it in there.
Wednesday.
Wednesday, good. Okay, so work on it over the weekend and then bring questions on Monday. Okay? Cool. Have a good weekend. Come to club meeting. I've got a feeling we have pizza.